Okay, here we are. This is part 2 on this Jolida stereo amplifier. We've got it powered up. There are no capacitors on the bridge rectifier output. So right now we're going to come on down and take a look at this oscilloscope. And here we can see we've got a power transformer secondary output of 790 volts, and we've got a nice signal coming off of the bridge rectifier at 254 volts. That's I think an average voltage. Probably should get a peak voltage for you, so we'll set it up on the next test to show the peak. We might be able to do that right now. Let's see, reading 2. Peak, enter, peak to peak. So right now, there's your peak to peak voltage is 390 volts on the bridge output. So that's what the signal looks like. We're going to add a capacitor and continue this this video. Once again, there's the amplifier. There's the breadboard. Our loads are right down here. There's a float meter. That's the actual DC. I guess you'd call that an average voltage of 251. Alright, so we're going to add a cap. Here's the caps. We've got two 470 450 volt caps that we're going to tie onto this bridge output, and we'll see how that affects the signal. Alright, so bear with me and stand by. Okay, the capacitors are tied onto the bridge. That's changed our DC average voltage to 324 volts. There's the two caps. The load is down there. They're pretty bright, light bulbs. Coming back over here to the scope, let's take a look and see how that affects the signal. Alright, we've got 670 volt peak to peak. You can see it's been clipped now. And then because we're showing a peak to peak on our B waveform, it shows 0. So we'll switch that back into go AC/DC. See how that. Alright, so there's our RMS at DC 323 volts. Looks like a pretty straight line, so those two caps kind of really leveled out that DC. But for some reason it clips the secondary. That A channel is connected directly to the secondary of the power transformer, and for some reason connecting those in just clips it right off. Don't know why. We'll try a different capacitor value and see if we can get this to change. So bear with me, we'll put another cap in. Okay, before we added the different caps, I wanted to capture the ripple voltage that's coming off of with the two caps connected, the two 470s connected, and we've got a ripple voltage right now of 4.5 ripple, and once again that's with the two 470s filtering the bridge output, and there's the two 470s still connected in. And like I say, the load, those 100 watt bulbs are still pretty bright, and there's 317 now DC average or DC voltage. Okay, we're going to change the cap to the smaller cap there. That's 220, I think, and we'll see how that affects things. So stand by. Okay, we've changed the capacitor. This is now the 220 microfarad capacitor. and we can see that the ripple has changed to 19 volt peak to peak, and our transformer secondary input to the bridge is now 680 volt peak to peak, and you can see the signal looks a little bit different the way it's clipped, but that's what the signal looks like. Let's show you the DC on that. Let's go ahead and change this. This will give us an RMS. Alright, so we gotta change the range. As our RMS is 318 volt. This is with the 220 microfarad capacitor. So there we have it. I guess we can try. We got the ripple. We'll go back and see if we can get a drawing for you so you can see what we're actually looking at and the way we're looking at it. But once again, here's the fluke meter reading 317, and that's with the 220 microfarad capacitor. So let me get some stuff changed around and we'll be back in a minute. Okay, we're back again. We've changed the capacitor now to one 470 microfarad capacitor, and there's the scope on the secondary to transformer. The input to the bridge, we got 660 volts peak to peak. Our ripple voltage off the bridge now with the one capacitor filter is 8.8 volt peak to peak. So that's what the signal looks like. There's the amp, and once again there's the power supply board. We moved the bridge rectifier off the power supply board and one of the filter capacitors, and we're tying these two clips. Those test leads connect right to the output from the transformer secondary, which is the power transformer at secondary. We do have the tubes installed just to act as a draw on the heater circuit, because that's also part of the power transformer. So the tubes are in this thing, and that's why you're seeing these load lines which feed off to 8 ohm resistors just connected just for safety, so that the audio transformers don't see any kind of spike. So we do have a drain load on those audio transformers with the tubes installed, even though there's no audio signal going into this thing. It's just a safety. There's the bridge on the breadboard, and there's the one filter cap, the 470. We added another meter here so you can actually see draw. There's a 770 milliamps of a current draw on this thing at 314 volts DC output. So that's what these light bulbs down here, again, they're pretty bright. That's what they're drawn, and which all goes back to why is that secondary on that transformer, the input to the bridge, now clipped. So we might take this back to no caps again to kind of finish it up where the signal looks pretty good, and try and understand what's going on here. So stand by. Okay, we're back again. We set up another configuration, so let's get started here. Once again, here's the breadboard, and this time we've got the two capacitors in series, and there's a voltage divider, which you can see on the breadboard. There's two small resistors there, and a tap off the center, and that goes to the center of the two capacitors, and then the outsides, one negative and one positive of each capacitor, goes to the positive and negative output of the bridge. So everything is hooked up. Let's turn it on and see what the signal looks like. Alright, light bulbs are on. Here we are. Our ripple is 17 volts. Our peak to peak on the secondary of the power transformer is 680 volt peak to peak. Again, we're still clipped. This shows our current and our DC voltage. DC volts is 322. That's the output from the bridge, and the current draw by the load of the bright light bulbs right there is 782-83 milliamps. Alright, so to give you an idea what this is looking like on a schematic, this is it right here. There's the transformer. The input to the transformer is 110 volt, or United States AC power. A scope are the pink markings, one positive and one on the one side of the output of the secondary of the power transformer, and one on the other side which feeds into the bridge. The blue markings are the channel B. The red was channel A. The blue markings are channel B, which is just the output of the bridge. On the right hand side you can see the little light bulbs there, and then down the yellow marking is the current meter, and the orange marking is the voltmeter. So it's pretty simple, nothing too extravagant. We're trying to understand why we're seeing this clip on that secondary. The first video take on this, there were no capacitors in the circuit, and there was no clip of the secondary of the power transformer. And then every time we add a capacitor, we get this clip back into the circuit. And that's, you can see the clip and the ripple of the series setup that we have right now. This is the Jolida schematic, and we're running right now as the schematic shows here. There's the bridge, and then they show the two caps, filter caps, output of the bridge, and then a voltage divider resistor network that they ensure that each cap is seeing the same voltage at that output. I think this was their idea of a safety margin for the capacitors, so that they didn't put the full 400 volts across any single cap. So they divided it in half, and each cap is seeing half of that. But the negative side of that is that we're seeing twice the ripple. I think this ripple is 17 or 18. Our lowest ripple with the two 470s in parallel was like less than 5 volts ripple. So this gives them a higher safety margin, but more ripple on the DC output. So once again, we had a suggestion from, actually I wrote to him and I asked him for any ideas on what could be happening here, and he suggested that we actually take the input going into the Jolida amplifier and put it on a Variac and vary that input voltage, hence the input voltage into the power transformer, and see what effect by dropping the input voltage, and also what you would do is drop the output voltage of that power transformer down, and see what effects that has on the signal. So we're going to set that circuit up next, and we'll be back in a minute. Okay, we're back. We got a new configuration here. We had a suggestion from one of the YouTube radio and electronic gurus. It was suggested by W2AEW that we place a autoformer or Variac on the input to the amplifier and change the input voltage to the amp and see what effect that has on the signal. So right here you can see the Variac. Once again, there's our current and voltage on the DC that's going to the load, and then over here once again we've got the signal, and we've got another meter here, and that's the actual AC that's being fed into the amplifier. The Variac is shut down right now, so it's showing 600 millivolts. But we'll change that and bring that up, and we'll see what happens here. So let's get started. We'll hopefully, right now we're starting to see some action here. Alright, so DC is showing 32 volts, 200 milliamps, and we're at roughly 20% on the Variac. And if we come over here to the scope, we can see we're clipping right now. There's 20 volts AC on the amplifier, and we can see that we've got 100 volts on the secondary of the power transformer and a 5-volt ripple on the DC output. This is in that standard Jolida configuration where we've got two 470 microfarad capacitors in series with a voltage divider across it. So this is Jolida's configuration right here, and you can see what's happening. And the question that we're asking is, why is that the secondary of the transformer, why does it clip when there's a capacitor on the output of the bridge? So let's increase this a little bit, and we'll get up to where we've got approximately 60 volts. You can see we got they're not as bright. Our DC output is 152, and we're running about 522 milliamps. And if we come over here and look at the scope, we can definitely see we got 330 volts on the secondary to power transformer with an 11 volt ripple off the DC output, and we're running 60 volts into the amplifier right now. Standard wall current is 120 right here in USA. So let's turn it up a little bit and continue to watch. But from what we're seeing here, this flatness or flattening or clipping or clamping or chopping off of the AC power transformer starts right at the beginning and continues on through. Well, let's bring it on up some more. Once again, the Variac, the power. We'll bring this Variac up to 100 volts. At 100 volts, the lights are getting brighter. We're at 268 on the DC bridge with 700 milliamps roughly output. That's the circuit. Once again, there's the two capacitors in series with the voltage divider included. There's a voltage divider. You can see the two little resistors on there. I think they're 150,000 ohms. So it's just a small voltage divider. The amp. And then here's our output at the 100 volts input. We've got 560, 570 peak to peak on the secondary transformer, and a 15 volt ripple. So there you go. We'll crank it all the way up so we can duplicate wall circuit. Okay, that's roughly wall circuit, nice and bright on. Okay, we cut out there for a second, but we're nice and bright on the bulbs. Once again, this is wall circuit power with 788 milliamps of current drawn by the load, 326 volt DC output, and our circuit looks like this. We got 122 going into the amplifier. We've got 680 volt peak-to-peak output from the power transformer on the secondary side of it, and we've got 17 volt ripple. So it's kind of obvious that the best way, or the best circuit configuration, was having those two caps in parallel, because we were down to like 4.5 volt ripple. I think the reason Jolida uses this configuration is a safety margin on the caps. It's probably a little bit better. You're dividing the voltage that you're dividing that DC 324 volts in half, so across each cap. So safety margin. Okay, once again, we're back. The safety margin is there, and this is the circuit, the way we're actually measuring it. Once again, the pink is the channel A of the oscilloscope, the blue channel B of the oscilloscope, the yellow is the milliamp meter, and the orange is the meter that's measuring the DC at the load. On this drawing, I'm not showing the that meter that's measuring the AC input to the amplifier, because that's a new configuration. Once again, that was recommended by W2AEW, one of the gurus on YouTube. He's an R&E guru. I contacted him via mail, and this was his suggestion, so we can see what this, when it begins to clip. And it's obvious that the clipping occurs right from the get-go. So if anyone understands why this AC signal off the power transformer flattens out and robs us of that little bit of extra power that we might gain, I would like to hear from you. Next, I think we're probably going to try. Oh, by the way, the diodes we're using, these were from Mosier, I believe. And these diodes are DG P30-E3/54. Alright, so that's the diodes we're using. They're a 1500 volt diode. So there you have it. We got some different diodes. Maybe we'll conclude this as part 2, and we'll move on to a part 3. Maybe try some different diodes. Maybe if we got some YouTubers out there that have a suggestion, we're willing to give it a try. What we're trying to do is we're trying to find out why we're getting a clipping or a chopping off of that AC signal. It seems to be robbing us a little bit of power that we could have that would go to the plate circuit, and there you have it. Okay, we'll be back when we get some new information and some new test setups.